we talk about a proportion, we are talking about the part of a group which can be classified in a certain way. Humans under age 21, states with more than 10 million residents, yellow Sour Patch Kids, registered voters who intend to re-elect a certain office holder. Proportions are the classic form of categorical data. If we take a representative sample and find the proportion of a certain trait within that sample, we can set up a confidence interval for the prevalence of that trait in a population. That interval is likely to contain the population's true proportion for this category. Before we start cranking away on our calculations, the sample and data must fulfill 4 important rules. Number 1, the sample must be a simple random sample drawn from a well-defined population. Number 2, the result in any single case must be defined as a yes or no. Yes, this one is a yellow Sour Patch Kid. No, this one is not. Yes, this person is voting for this person. No, this person is not. Number 3, there must be at least 5 yes responses in the sample. And number 4, there must also be at least 5 no responses in the sample. Once we recognize that all of these have been fulfilled, we can start setting up the interval. Our point estimate is p hat, the proportion of the sample of size n which is positively included in the specified group. To set up the interval, we need 2 numbers, a critical value based on a desired confidence and a standard error. The product of these 2 numbers is our margin of error. The standard error is the more basic of the 2. Take p hat, multiply it by the complement of p hat, which is 1 minus p hat, sometimes called q hat, divide this product by the sample size n, then take the square root of the whole thing. The critical value is determined by the degree of confidence we wish to have in the interval. We cannot be 100% confident that any interval short of the entirety of 0 to unanimity contains the true population proportion. Instead, we declare a certain degree of confidence. Common ones are 90%, 99%, and especially 95%. We of course cannot set up an interval which contains a set amount of the distribution of results on the population value itself. By definition again, that true population parameter is unknowable. But what we can do is set up an interval on our sample result with the understanding that if we take many sample results and construct many intervals, we can expect 90% or 99% or 95% of those intervals to contain the true population proportion. So we determine how many multiples of that standard error are required to cover that spread in an assumed distribution. That multiplier is our critical value. Take your z-table. Subtract your degree of confidence from 1. This result is called alpha, which is useful now, but will be much more important when we talk about significance tests. Because our result is centered, we will be leaving off half of the distance on the high side and half on the low side, so divide the alpha by 2. Find the z-score, which corresponds to the proportion defined by that half of alpha. That's your critical value. Common critical values are 1.645 for a 90% interval, 1.96 for a 95% interval, and 2.576 for a 99% interval. Multiply the critical value by the standard error, add and subtract this result to p hat, and you have constructed your confidence interval for the population proportion given a certain sample result and a stated degree of confidence. Let's run through an example. In a bag which contains 60 M&Ms, 12 of them are brown. What is the 95% confidence interval for the prevalence of brown M&Ms in general circulation? We check against our requirements. We can assume that this bag is a completely random filling from the thousands or millions of M&Ms made every day. An M&M is either brown or not brown, so there's our binary. We have 12 positive responses and 48 negative ones, so we have an adequate sample. We may proceed. First we find p hat. 12 over 60 is 0.2 or 20%. Our critical value for a 95% confidence interval is 1.96, and our standard error is the square root of 0.2 times 0.8 divided by 60, or essentially 0.01564. Multiply those, and we get 0.1012. Add and subtract that to our 0.2 point estimate. Our 95% confidence interval for the proportion of brown M&Ms in broad circulation is between about 9.9% and 30.1%. Needless to say, this is not a staggeringly precise measurement. If we want to narrow down the interval, we have 2 options. First, reduce the confidence interval, or, second and more technically effective, increase our sample size. If we have a larger sample, then the standard error works out to be smaller as we're dividing by a larger number, and conceptually it's a better representation of the population, which is of course the entire aim of this exercise.